Good day, class. So this is our last topic for integral calculus for this semester, and this concerns the multiple integrals. Now, for this set of slides, we will only focus on the evaluation of the multiple integrals and the properties of such. So as to the application of this, so as it won't be that overwhelming to everybody, especially now that we are on virtual learning and then you're just accessing all the reference materials and all the uh, PowerPoints and all the recordings via Canvas, and there's no face-to-face interaction with me. Now we have decided that we will leave the application of this topic in your professional subject later on, depending on the need that may arise. So what's important, as I've said, is just you will know how to evaluate the multiple integrals and their properties. Okay, so of course it is important for this particular set of slides and for any set of slides so far that we have discussed that we will define our learning objectives. So at the end of this particular set of slides, you should know how to evaluate the double integral, a triple integral, and discuss the properties of such, or apply the properties of multiple integrals to the varied uh, multiple integrals that you will be evaluating. Now let's start with the double integral. Now you will see in references, especially PDF copies, since I'm sure not everybody here have a hard copy of the book. So you could see that the limits of integration for multiple integrals is just represented by a particular letter. Most of the time, that particular letter is capitalized. So in the case of this particular double integral of the function of x and y, integrated in terms of the differential of the area, the D that you see here is representing the boundary of any region. So if you are evaluating a double integral, you are actually evaluating the area bounded by this particular D region. Now this D region, of course, has to be specified as to what boundaries it has. So for example, how is it bounded on the x-axis? How is it bounded on the y-axis? So that's very important. But nonetheless, just for a simple way of writing the two sets of limits here, we just write the D. But the D represents the boundary of the region in which we want to determine the area of. So the double integral is used to integrate over a two-dimensional region only. And since it's a two-dimensional region, then we are concerned with the area of such particular region. Now this dA, by the way, is changed into, let's say for example, since you have the function here x and y, this is changed to the product of the two differentials dx and dy. So it's just represented here as dA so that it would be simply written simply. Okay, now as for, let's say, an illustration so that you will find the significance of, or the essence of having to know the process of double integration or evaluating a double integral. Let's say you are asked to determine the area of this particular uh, region bounded by this curve in red, which is y equal to g sub 2 of x, and this curve here, the blue, which is y equal to g sub 1 of x. Of course, you know how to determine the area of this using the principle of plane areas. But in terms of the application of the double integral, that could also be evaluated using this new concept of double integration. So the D region in here, which should be bounded or whose boundary should be in terms of x and y because this is a plane. So this is your x boundary and this is your y boundary. In terms of the x boundary, it will have to start from A up to B because in terms of what the illustration tells you to determine, it should be bounded on the x-axis by from A to B only. So this is our boundary for the x-axis. As for the y-axis, the vertical axis, that would be then the equation of the upper curve. That would be our g sub 2 of x, and the lower curve, the g sub 1 of x, because these two are representatives of the y's of the points in this curve, the highest curve, and the y's of the points on this curve, the low curve. So we have to start with g sub 1 of x because it's the low curve or the lowest curve, and then end with the g sub 2 of x. Or simply put, in terms of the vertical axis, your y is bounded by, okay, common sense, is bounded by this curve. The upper part is bounded by this curve, and the lower part is bounded by this curve. So that's your y. So when you write the double integral, generally it would be written like this: the function of x of and y dA. Then you have the double integral and the d, which is specified in here. But when you evaluate already, there is a need for you to write down specifically the limits representing the boundary on the x and on the y axis. Okay, so this is how we represent the area. So the function of xy dy. So since we started writing the differential of y, the limits that will be reflected on our first integral will be the boundaries for y. So it would be from g sub 1 of x to g sub 2 of x. Then the next integral is bounded by x, since we have the differential of x here. So it would be starting from a here to b. Okay. Now question, can you interchange this one? The answer is yes. So if you interchange your differentials here, you have to interchange as well the limits of the integration. When you interchange, it should be based on the fact that it would be easier for you to evaluate this expression. For example, if you do the exchange of the differential or the interchange of the differential. When you are integrating in terms of y, in the case of this particular general representation, all the x variables that you will see in this function of x and y are considered a constant. Okay? When you integrate in terms of x the same way, all the y variables are considered a constant. When you substitute your limits later on, the limits will only be applied to the particular variable that you base your integration process on. Okay, now let's see another case. This time you want this area, you want to know this area, and it's bounded on the farthest side by this curve x equal to h sub 2 of y, and this blue curve which is h sub 1 of y. Okay, on the vertical axis, on the y-axis, it's bounded by the point C to D. So you could see here the D now defined. So the region D for this particular curve you want the area of is bounded on the x-axis by h2 of y, or from h1 of y to h2 of y. So these are your boundaries. Now as for the y boundary, then that would be starting from C to D. Okay, you could see it here. So when you write the integral now specifically, you know this is how generally we can write it, but when if you want it specific already, you can start with dx, then your limits will be starting with h1 of y to h sub 2 of y, then followed by dy, which will be having the lower limit c and the upper limit d. So take a closer look that if you interchange these two, just like in the first case, you have to interchange the set of limits that you're using in your integral. Okay, let's have a specific example. By the way, we first discussed the properties. Before we evaluate specific examples, we will discuss the properties of double integrals. By the way, these properties are also applicable for triple integrals. So let's say you're given this. Actually, these properties are also the same or comparable to the properties of definite integrals. So let's say, for example, you have two terms here, or you have the sum of two functions f of x and y and g of x and y. You can evaluate separately these functions and then add the two double integrals after evaluation. Now, if you have a constant in the case of property number 2, multiplied to a particular function, just like the definite integral, you can set aside the constant before the integral symbols and then process the function that you have on the right side. This is applicable only when c is a constant. Now let's say we will separate the D region that we have defined in the first two cases specifically into two separate regions. So then we can say that the integral of these two can also be the sum of these two separate regions with their specific set of boundaries. So what you could see here, the same function, let's say for example, just one function, the function of x and y dA, and it is bounded by this region. We separate it into two regions. So the original double integral is equivalent to the sum of these two integrals whose limits or whose regions are actually comprising the original region which was separated into two. So you have here D1 and D2. So these three properties, together with what I've mentioned a while ago, that you can switch the manner of integration as long as it would be easier for you to go about the evaluation if you do the interchange, that could be added to what you already know here. So you can change from dz to dy or dy to dz, from dx to dy to dy dx, as long as when you interchange, you also interchange the set of the limits of your integrals. Now let's have this first example. This is easy. You have this particular double integral, and it's an exponential function e raised to x over y dA. Now we now change the dA into the d of x and the d of y. Notice that it was really written here that it should be dx dy, not dy dx. If you place the differential of y first, followed by dx, you are required to integrate this exponential function e raised to x over y in terms of y first. If it's in terms of y, your variable then, let me annotate, your variable then will be y. So it would be like saying, it would be like saying you have e integral of, let's say I will change the x into a constant because the other variable will be considered a constant. Let's say it's 2 over y dy. This is in the case when you opted to do dy first, then dx here first. Now, what can you say about this integral, regardless of what is written here as the limit? Can you integrate this exponential function if you started with the variable y as your first variable to be integrated? And the answer is no, because your u here is 2 over y. And for you to answer an EU here, its derivative, the du, should be placed in here together with this exponential function. And we know that the derivative of this is negative 2 over y squared. And we don't have it here. So what I'm trying to say is if you change the manner of integration, let's say you change it to dy dx, and of course you will change this, you change this to 1, to 2, and then your y and y cubed would be here, your y, and then your y cubed would be here. It would be resulting to evaluating a non-elementary integral. This becomes a non-elementary integral. Okay, and that would be difficult to evaluate. In this case, however, let's say for example, you're not required. You're not required to show the complete solution of the evaluation of this. And since your limit now, right here, your limit would be e raised to 2 over y dy. And you have the limits 1 to 2. Though this one is a non-elementary integral, this one can be processed by your calculator. Why? Because the limits that you have here are real numbers. Should the limits that you have here, let's say for example, be variables or a combination of variables and numbers, then this non-elementary integral will not be or can't be evaluated. In here, it's okay if you will interchange because the limits that you will be using are real numbers. So you only have your calculator, Mr. Casio, to thank for because this can be evaluated by your calculator. Once evaluated, then you can do the next integration, which is in terms of dx. Okay? However, let me stress that or emphasize that should the limits here be not numbers, but rather variables or combinations of variables and numbers, then you cannot do the switch of having to integrate first with respect to y, then followed by integration in terms of x. So we'll go back to the original expression that we have. This is our original expression. And we will integrate in terms of x. So this y is a constant. Then in your e raised to u expression, your u is x over y. And if you're integrating in terms of x, the du would simply be a 1 over y because you're integrating in terms of x, y is a constant. Since it's 1 over y, what you did actually is you place before the integral a y over y. That way you can use the 1 over y and the y is here. Or it's like you have written here y over y. The 1 over y you made use as your, by the way, there's a dy here. You made use as the derivative of your u, and the y is this y that you are seeing here. So you have y e raised to x over y. Limits would be y to y cubed. Remember, since you are integrating with in terms of x, you will substitute the y and the y cubed to the x only in here. So you have y e raised to, so if this x is y cubed, you divide it by y, that would be y squared. Okay, then minus y e raised to, if this is x is equal to y, so y over y is equal to 1. So what you did, you substitute for the, I'll use a different color. You substitute for the x only. You substitute for the x these two. The y is kept because it's a constant. So this will be your answer. So you have, I'll just give one specific example here. That way in the next, you would know how it's done. So I'll change to a bigger. So in this case, you will have y e raised to this x that you have here will be changed to y cubed. So that's y cubed over y minus, again, y e raised to this x here will be y over y. So this cancels, that leaves here 2. This cancels, that leaves 1 for the exponent. So this is the expression that you are seeing. But you're not done yet because you will do the next integration in terms of y. When you integrate this first expression in terms of y, the derivative of the u here, which is y squared, is 2y dy. So there's a need for you to place 2 and then 1/2 here. The reason why you have 1/2 here, e raised to y squared. This one, the expression 2y is the du of the y squared. Now, if you integrate here in terms of y, that would be y squared over 2. This is just a constant, which is e. So y squared over 2. Now, don't forget that you still need to substitute the limits 1 to 2. So you substitute 1 and 2 to the y. So in this case, you will have 1/2 e raised to 2 squared minus 1/2 2 squared e, this is for the upper limit, minus the lower limit, which is 1. So you have 1/2 e, that would be 1 squared is 1, minus you have 1/2 1 e. So you have 1/2 1 squared is 1 e, so that would be e. Okay, so this entire thing cancels itself. This one is this, and this one, we cancel 1 here, you have 2e. So this one is the answer to the area represented by the curve e raised to x over y. Okay, bounded by these two sets of coordinates in the x-axis. You have y cubed, y and y cubed, and on the y-axis that would be 1 to 2. Okay, so what you have determined here actually is the area of the given curve, bounded on the x and y axis by these limits here. Okay, that's what you're after. Okay, so let me clear the markings here. So this is our first example for double integration. We'll go to the next. Now, for this next problem, the D region is not specified, but it's mentioned here. Let me annotate that it should be bounded by this curve or these two curves. So meaning the D region that should be placed in here, the boundary of the region that should be represented here in terms of the limits will be bounded by these two curves. So how would you be able to write down the set of limits here? Okay, the first thing you do is you graph. So graph. This is the graph for the y equal to the square root of x. And this is the graph for the y equal to x cubed. Okay, I'm sure everybody knows how to graph. When you graph, then the next thing that you do is, since you know already that in terms of y boundary for this area, this is the y boundary already. Because this is y equal to x cubed. That's the lowest set of points. And this is y equal to square root of x, the highest set of points. You did not worry about the y boundary that you will place in here. Wherever you will place the dy, so that's where the corresponding limit square root of x and x cubed should appear. Now, in here, it's first written as dy, so you notice that now you have written x cubed for the lower limit and square root of x for the upper limit. The big question is, how is this 0 and 1 determined? How was 0 and 1 determined? So if you recall our discussion on areas between two curves, plane areas between two curves, for you to be able to determine the intersection, of the two curves, you have to equate. You have to equate both sides, or rather you have to equate the equation of your curve. So when you equate y equal to square root of x to y equal to x cubed, it would be something like this. Oh, sorry, x cubed. It's only x here. Okay, now since we have a square root of x here, might as well square this. So we square and you will have x equal to x raised to 6. So you will have, if you cancel this one, you have 1 is equal to x to the 5th. Then x is equal to 1. What's the 5th root of 1? That's 1. So you have 1. And then what other number would be written here? So you already have 1 here. That's the upper limit 1. Now, how did you know that this would be like 0 in the lower limit? Hey, well, why would it start from 0? Okay, now in this case, if you place 0 in this side, if you substitute 0 here for the x, and this 0 will be raised to x, both sides would be equal to 0. 0, 0. 0 raised to 1 is 0. 0 raised to 6 is 0. So both sides will be equal to 0. Or, better yet, you substitute an x value here, which is 0. Your y will be 0. You substitute an x value here, which is 0. Your y will be 0. So it's true for the two cases. So your boundary in this case would be, in this particular problem, for the x is 0 to 1. But I'm just discussing this for the sake of you understanding the essence or the importance of the double integration in determining areas. Now, when you will be asked to evaluate here double integrals, you need not determine this, let's say, points of intersection between the two curves. That way, you will know how the curve is bounded, either on the x-axis or on the y-axis. You will simply be, in this topic, required to evaluate the double integrals. In this case now, I will have to erase this one. You will just, or our focus is just on the evaluation of this double integral. But I hope you did understand how we determine the boundary of these two curves, the area between these two curves on the x-axis. So when you integrate this in terms of y, x is a constant, so this would be y squared over 2. So that explains that you have 2x left here. And this would be y to the fourth over 4. So that's it. Then you substitute the limits. Okay, now let me erase this part here so I can write how that particular answer there in the second line came about. Okay, so you will substitute square root of x for the y's because you integrated in terms of y. So what I'll do now, I will substitute the variable x, square root of x for the y. So for the first part here, in here you have 2x. This y should be square root of x, and this is squared, minus 1/4. This y is square root of x raised to 4. That's for the upper limit. Your lower limit is the x cubed. So it should be 2x x cubed squared minus 1/4 x cubed, x cubed, class. Where was I? X cubed, we raise this to 4. Okay, so if we will simplify this, this would be 2. This is x times x, so that would be x squared. This one would be minus 1/4. Squared is already x. When you square it again, that would be x squared. This one is 2x x cubed squared. So this would be x, this is squared. This is x raised to 6 times x, that would be 2x raised to 7. And next would be this one. You have 1/4. You have x cubed raised to 4. So that would be x raised to 12. So minus 1/4 x raised to 12. Okay. These 2 minus 1/4 is 1 3/4, and that's equivalent to 7/4 x squared. So you have combined these two to get this. This is copied from here. And by the way, this is minus, and we're already on the lower limit, so this should be plus, minus, minus, plus. So now these two terms are this one that I have written. When you simplify, when you substitute, or this one is simplified by integrating first and substituting the limit. So when you integrate, this is x cubed over 3. So this makes it 12. This one is x raised to 8 over 8. So that's, you have the 2 here. So that's 1/4. And this is x raised to 13 over 13. So 4 times 13, that would be 52. If you substitute these limits here, the answer will be 55 over 156. That would be representing the area bounded by these two curves, y equal to square root of x and y equal to x cubed, using double integration. Okay? That's very clear. I hope that's very simple. Only that the difference of this particular problem from the first is that the exact limits still was determined by you. These are already given in terms of the y's here, but this one you determine using the intersection of the two curves bounding that is the boundary of the region that we want to determine the area of. So actually it's written also here that your x will be from 0 to 1 and your y will be from x cubed to square root of x. Now let's move on to the next example. Now, this example allows you to find the area outside the circle r equal to 2 and inside the circle 4 sine theta. The region is described by theta from pi over 6 to 5 pi over 6. And the r, of course, this is the r, is from 2 to 4 sine theta. So if we will write the area bounded by this region, these two regions, this is by the way the illustration, and okay, let me annotate. This is your r equal to 2 circle, and this is your r equal to 4 sine theta circle. So the region that we're interested in is this pink region. Anyway, the problem already specifies the boundary. So in the case of the objective of this set of slides, given the boundary, so your r is bounded by the equation of the r's, of the radius of the circles in terms of r, and this is the theta. How do you find the theta? It's the same thing as you find the intersection of two lines. So you equate this r and this r expression here. So I will illustrate it here. So you have 2 is equal to 4 sine theta. Okay, we equate the 2r. You divide by 4 in both sides. That would be 1/2 is equal to sine theta. Then theta is equal to pi over 6. That's 30 degrees. If I'm going to draw here, it's not actually, I'm just using this particular axis to illustrate. This is your, let's say for example, this is your 30-degree angle, or this is your pi over 6, which has a sine of 1/2. But in here, if you have this one, this is 150, right? 150 degrees. The reference angle is still 30 degrees from here, but negative already because it's measured from the x-axis in clockwise manner. So I'd like to erase this part because we measured the angle in clockwise manner. When we measure the angle in clockwise manner, the sign would be negative. So this is, if you're going to measure the angle in that manner, that would be negative 30. The entire angle here is 180. This 30-degree angle is having a sine of 1/2. This negative 30-degree angle is also having a sine of 1/2, even if you're going to check it in your calculators, because the y-axis here is positive. So in that sense, the other angle that you can place here equivalent to negative 30 degrees is the 5 pi over 6 angle. So you subtract from 180 pi over 6, so that would be 5 pi over 6. So you have these two theta values. The values that you are seeing here for the theta. Okay? But again, when you evaluate double integrals, if it's just pure evaluation, these limits will be provided to you. If it's not in the near future and you will be asked to determine the area bounded by these two circles, as it is described here, then you ought to know how to find the theta. You just simply equate the equation of the two circles in terms of the r value, because the r here is equivalent also to the r in here. Okay? Why would you say, Miss, that the R in here would be the same as the R in here? Because we're actually looking for a point in this equation of the circle in which the r and the theta would be equal. And as such, we have equated these two equations. So this is our answer. That would now comprise the limits on theta or for theta. Okay, so if I will clear my markings, I will just clear this one here and this one. Then if you will integrate in terms of r first, then it would be r squared over 2. Then if you substitute the 4 sine theta and 2, that would be 8 sine squared theta minus 2. You're not yet done because you are still to evaluate in terms of theta. So I mean, you evaluate in terms of theta if you really want to know how this integral should be processed. This should be undergoing trigonometric transformation. Or if your calculator can do it for you, then why not? Because you have here actually a real value. So all you have to do is encode this in Mr. Casio. He will already give you the answer without you knowing in the first place how the integral should be evaluated. Meaning what I'm trying to say here, even if you don't know how to integrate this one, since you are given a definite integral, your calculator can process this for you. Now, it's a different story if it would be required from you the solution of the answer for this particular integral. Okay, so the answer is 4 pi over 3 plus 2 square root of 3 for the area of this pink region. So I'm sure you know how to substitute your 4 sine theta to the r squared. That would give you 16 sine squared theta since you divide by 2, so that would be 8. For the lower limit, you have 2 squared, that would be 4 divided by 2, so you have 2. Okay, the rest is substitution of the pi over 6 and the 5 pi over 6 to the theta, but that is after you have done already integrating. You need to integrate this first. After that, you substitute these sets of limits. Okay, so I think the 3 example would suffice us to illustrate how a double integral should be evaluated. Now we go to the triple integral, because when we speak of multiple integrals, we should know how to even okay, evaluate a triple integral. So the triple integral is used to integrate over, this time, a 3-dimensional region. So if in a double integral, one application could be finding the area bounded by curves or functions. In the case of the triple integral, we are concerned with the volume. But these are just examples of their applications. There are many applications of the double and the triple integral. Now, let's start by simply finding the region, the B region, for a particular rectangular box. So the B region for that particular rectangular box is bounded on X by AB. So we have X first, bounded on Y by CD, and bounded on Z by RS. So note that in the way we write the notation for the boundary of the region, for a 3-dimensional region, we start with X followed by Y and then with Z. When we want to find the volume of such a region, now we are after the integral of the function of not just 2 variables, but 3 variables, X, Y, Z. And as such, this dv can be a combination or a product of the 3 differentials dx, dy, and dz. Now, as to what particular limit would appear here in your integrals, that would depend on what differential you're writing first. When we do multiple integration, we always evaluate starting from the inside going out. So you start evaluating with the differential of x, followed by the differential of y, then followed by the differential of z. Note that in this case, we have integrated with respect to x, then y, and z. But actually, this is not the only way in how we go about finding the integral or evaluating this triple integral. There are 6 different possible orders in which you will do your integration. You can start with dy dx dz, or you can have dz dx dy, or you can have dx dz dy, and you can have dy dx dz or dy dz dx. You have 6 different possible orders, all of which will be giving you the same answer. Now, the only thing that will be a challenge here, you find the order that will make it easier for you to integrate. I think I have explained that using the first example, that when we interchange the manner of integration, it will have an implication on the way we do our integration, especially if our limits are not real numbers. Now, if our limits are real numbers for that particular integration process that you are doing in that particular order that you have chosen, you won't have any problem if it's a real number because your calculator can do that for you. But if the limits are not real numbers, then that's the big challenge, because you should know how to process or evaluate your given integral with the challenge of thinking of the appropriate technique to use, especially if it's not easy. So in short, what I'm trying to say here is you choose the order that will simplify the process of integration. Okay, so let's start with this simple example. So we find the volume bounded by this set of points here, 2, 3 for the x, 1, 2 to y, and 0, 1 for z, for this particular rectangle. So 8x, y, z. So since 8 is a constant, you can write it before the integral, but in this case, you can have it here because anyway, it will not be anyway cumbersome when you do the integration. In this case, we did integration with z followed by x and y. So you have to use the 0 to 1 limit for the z, then followed by the x, which is 2 to 3, and for the y, which is 1 to 2. When you integrate in terms of z, the x and the y are considered constant. So if you use power rule here, that would be z squared over 2. That would give you 4xyz squared. Then you just substitute the limit 0 to 1. 0 will automatically give a 0 answer. So your answer here would be 4xy. Next, you integrate in terms of x. So x squared over 2, so that would be 2x squared y. Substitute the limits 2 to 3 for the x. That should give you an answer of 10y. Then you integrate again, that would be 5y squared, because this one would be y squared over 2. Your 5y squared, when integrated from 1 to 2, or rather when we substitute the limits 1 to 2, because we're done with integration, the answer would be 15. So in here, we're finding the volume of a rectangle. Okay, now the same example, this time we change. In here, we start with dz dx dy. In here, we have dz dy dx. So here is the general way of how to do it. And in terms of a specific example, so these are your limits. Now, what is the problem in the first place? So we use an integral to compute the volume of the box with opposite corners at 0, 0, 0. So one corner of the box is at 0, 0, 0, the origin. And the other corner has its x on 1, its 2, its y on 2, and its z on 3. So telling us that on the x, the highest point is 1, the lowest point is 0. On y, it's 0 for the lowest point, the highest point is 2. And on z, the highest point is, the farthest point rather is 3. And of course, we have the origin to start with. So when you write the limits, all will be having 0 for the lower limit. So this is for z, this is for y, and this is for x. And of course, you know how to do it. Since we don't have any variable here, so it's just a simple case of integrating the differential. So you'll have a z, then we substitute the limit here, that would be a 3. So we have a 3y, Then we substitute the 2, that would be a 6x. 6x times 1, that would be 6. Automatically, the lower limit 0 will be a 0. Okay? Now, next, this particular integral that I've shown you actually determines the volume of this tetrahedron. Okay, I just place in here the illustration. So you will learn when you go to your, I think, I don't know if it's in electromag, but there's a particular subject for electrical engineering students and for ECE where you are the one who are determining these limits for a particular three-dimensional figure. Now, you are just taught here the tools on how to evaluate, but when you go to later on to that particular professional subject, you will really be the one to determine the limits here. So that would be the goal of your teacher there, to teach you how to determine this one. Our goal here is for you to know how to integrate only. Okay, so when we integrate in terms of z, so we have a z and we have this limit. So then we have a 5x over 2. Then we integrate with y. So 5xy over 2. We substitute the limits 3x over 2 and 3. That would give us these two expressions. Our last integration process would be in terms of x. So this would be 15x squared over 4 and 15x cubed over 12. If you substitute 2, because 0 will automatically mean this is 0, that would give you a 5 for the volume of this particular tetrahedron. Okay, now I think this is our last sample. Okay, our boundary for the x is from -2 to 1. For the y, it's from 0 to 3. And for the z, it's from 1 to 5. So we just place it here, 1 to 5. And then we have x, -2 to 1. And then we have y, 0 to 3. The box that we're talking about is this box, the rectangular box. So if you integrate in terms of y, so that would be x here, that would be x squared y squared over 2z. And then you will substitute, I think, by the way, which one? X squared, you're integrating in terms of y, so this should be y squared over 2. There's a mistake here, class. Y squared over 2, then you substitute from 0 to 3 for the y. And then you integrate in terms of x, so that would be x cubed over 3. By the way, here it is, by the way. Okay, here it is, x cubed over 3z. Then you have, for the z, then you have this one, and that would be a z squared over 2. The answer is 162. Now, when you do the integration in a different manner, the sequence is changed. In this case, you have dx, dz, dy. In here, you have a dy, dx, dz. The answer would be the same. It should be the same as long as you did it correctly. Okay? So in here, you are integrating in terms of x, so that's x cubed over 3, yz, -1 to 2. So this is the answer. When you integrate in terms of z, that would be c squared over 2, substitute 1 to 5. So this would be 36y. And if you integrate this, that would be 18y squared. 36 over 2, that would be 18y squared. Substitute the 3 for the y squared, that would be 9. It's still 162. So basically the same as the one that we have here. Okay, it's the same as the one that we have in here. So it would be giving you an answer which is 162. I think there's a typo error here, because if you will integrate in terms of y, let me just annotate here so you have a correction. This will be Your next integral would be 1/5. You have negative 2 to 1. I'll just copy this one. So x squared z. I will have the y to be y squared over 2. Okay, y squared over 2. And then your limits would be from 0 to 3. The next would be dx dz. Okay, let's say we'll complete this one. So you have 1 to 5. You have here negative 2 to 1. Negative 2 to 1. And if we have x squared z, and if we substitute 3 here, this would be 3 squared, that would be 9 over 2. dz dx. Or better yet, we will use the whiteboard because this one will clear the markings here. I'll show to you how we'll do this in the board. X squared yz. Okay, we'll copy. So we have the integral of x squared yz. So you have dy d, I forgot the order. Wait. We have dx dy. Dx dy 0 to 3. I just need the first. Dx dy. We have dx dz. dy dx dz. I'm a very forgetful person. dy dx dz. And then we're going to integrate from 0 to 3. So 0 to 3. I'll write the other integrals later. Okay. If I will process this, it's like x squared z. Then I have y squared over 2. Then we'll substitute the limit 0 to 3. So this would be x squared z. I'll divide it by 2 because it's just like one constant here. Then I'll substitute the y squared, which is 3. So this is 9 over 2 x squared, 9 over 2 x squared z dx dz. Our next limit that I will need to integrate is negative 2 to 1. So we'll substitute negative 2 to 1 for the limits for the x, negative 2 to 1. So if I will integrate in terms of x, that would be 9 over 2z. This would be x cubed over 3. And we will integrate from negative 2 to 1. So 9 over 2z, your x would be 1 minus, or 1/3, because we have here x cubed over 3. So 1/3, and negative 2 cubed will be plus 8 over 3, right? Because this would be negative 2 cube is negative 8, and it's negative because it's minus, so that would be positive. So this is 9 over 3, and that would be a 3. So this is 27 over 2z. We will integrate for the last time using the limit 1 to 5 for the z. So this one will be from 1 to 5 dz. By the way, when you write your integration process, the rest of the integral should be written. I did not just write it here because I keep on forgetting the limit. So if you're going to complete this one, this should be negative 2 to 1, and this should be 1 to 5. Okay, in here, you should have 2, and you should have another integral here, which is negative 2 to 1. Okay, I'll erase this. Because you may say that it's just okay. Actually, it's not okay. It's just that I am a forgetful person, so to simplify things, I did not copy the other integral. So this is it. Now, when you integrate that, I'll just write it here. So you have a 27 over 2, and your z would be z squared over 2, right? When you use power rule here, and this would be 27 over 4, and you have a 5 for the z, which is to be squared, minus a 1, which is to be squared. So this is a 27 equal. 27 over 4, 4 times 24, right? 25 minus 1. So let's check if it will give us the same answer. So we can cancel the 4 here, and this gives us a 6. So a 27 times 6, that's also 162. So the same answer with the second example without the typo error. Same 162 answer. Okay? So let's go to our slide. We still have this one. This part is correct, but there's an error here. There should be y squared over 2. Okay? Now, so we have the 162. So in the seventh sample here, it's the same integral. However, we interchange the manner of integration. So it's not really difficult to do multiple integration as long as, so let me explain, specify, as long as your limits are all real numbers. If the limits are not real numbers, then you really ought to know how to integrate the expression that is given. If not, when you substitute your limits, which are not numbers, you will have difficulty getting the right answer. Why am I saying that it's a lot easier when you have the limits expressed in terms of a real number? Because you need to show the process. Your calculator can do that for you, even if you're provided with a non-elementary integral. So in this case, you should know how to integrate. In the seventh and in the last example, there's no need for you to know how to integrate. Why? Because you have a limit here, which are all real numbers, and this is just very simple. It's just power rule. Okay. What I mean we really know how to integrate is that you have already developed the skill of how to process integrals which are not simple, meaning you have to use the appropriate technique. Okay, let me check. So far we have covered everything in terms of the evaluation of the multiple integrals. And in part, I have discussed to you the significance and the importance of multiple integrals. Multiple integrals have a lot of application, including determining the center of mass. Aside from determining areas and volumes, there's a lot of examples for multiple integrals. That would be your next topics in your other professional subjects where you will be encountering it. Here in Calculus, our goal is for you to just know how to evaluate and maybe give you a backgrounder on the significance and importance of what you're doing here. That way, later on, when you encounter the same application, the same said application, you will not really have a zero knowledge about it. Okay? I hope you will listen to this together with the other recorded discussion on the topics. That way, when we do feedbacking, you can write down any questions that you may have. That way, I can address those questions. Okay, class? Thank you for listening. Till we meet in class, and for you to share to me your concerns regarding areas in the topics which you think you were not able to fully understand.